So V over here, we know that this is equal to what? 0. At X, 0 will equal to 0. Because there's no support over there, yes? So it's 0. Okay. How about M? What is M equal to? Anyone? Anyone? What is our moment at point A?
0.
Yeah, 0. And why it is 0? Okay. Why is it 0? Because when point B is removed, right? When point B is removed, the structure will rotate. Okay. And I don't want you all to worry about the other boundary conditions or theta and y because we have not learned slope and deflection yet. It's okay. Okay. After the break, we'll come to it. At B, can someone tell me what is the shear force and what is the moment? Anyone? At point B when x is equal to 6 meters.
72,000.
I don't know yet.
The equivalent load.
Okay. The only thing I know, okay, the only thing I know that this is Vmax and this is Mmax. What values they are, I have not a clue yet. Okay, but I know that one will be Vmax, one will be Mmax. Okay. So, and the other one that's very obvious, the deflection is equal to 0. Okay. So what we have done is we have formed boundary condition. So this is boundary condition number 1. And this is boundary condition number 2. So boundary conditions are at specific points. You know the values. Does not need to be 0. Okay, does not need to be. Okay, sometimes it can be a magnitude. Okay. So now, why strength of material is more difficult? Because you have to form omega x. Okay, so in terms of math, you guys are always given this, right? So y as a function of x is equal to 32x cubed plus by 6x squared plus by 2x plus by 1. And then the math instructor will tell you when y is equal to 0, it is equal to 0, and y is equal to 1.5 is equal to 7. And then yourself get your marks. Most of you get A's, come, and then you enter this class, right? That is math, right? So it's very what? Procedure based, okay? You just look at textbook or her notes, okay? Then you just, okay, we do this, integrate, okay, put this boundary condition, and then boom, boom, answer is out, right? In strength of material, you're not given an equation at all. You're just given a figure and some numbers, right? And then there's no boundary condition, right? So you have to form all these boundary condition on your own, okay? And that's why it is so integrated with physics and math, okay? So this is one reason why strength of material is not so straightforward, okay? Down here is very what? Procedure based. Okay, over here, no more procedure. You need to what? Analyze, okay? Right? Okay, so now we are going to solve this now, okay? So so let me write down the solution procedure for you guys. Any questions so far?
Professor,
Yes.
could you go back to the diagram on the
Yes.
previous page? Sorry, why is y equals to 0 at x equals to 6?
This is because it is built in, so it cannot move.
What is y? Why is the
Deflection.
Okay, downward deflection. Okay.
Yeah.
Thank you.
Even sideways, it also cannot move.
Okay, yeah.
Left and right also cannot move, okay?
Yeah.
Okay, so this is x, this is y, okay? Right. So now we are going to look at the solution procedure. Okay. And I'm going to write out the solution procedure, okay? If we use the integration method, and I want you to also compare, okay? I also want you to compare later on the solution procedure that we use for integration method and the solution procedure if we use positive shear and positive bending moment. So I want you to see the difference, and I want you to know the difference. Students get confused because they thought both of them are the same. They are not, okay? I mean, there are similarities, but there are difference, okay? So now, first of all, we have to find the equation of the distributed load. Okay, and then we are going to substitute. Okay, we're going to substitute. Okay, so this one, when we find, we know our omega is a function of x. Then we're going to substitute into dv over dx. Okay, and this will be equal to minus omega as a function of x. Okay, then from here, we are going to integrate the first time. Okay, 1. So when you integrate, now over this side is v as a function of x. Okay, so when you integrate, this will be equal to minus omega as a function of x dx. Because there's no limit, okay, I did not put any limits down here, right? There's no limits. So you need to do plus c1. Okay, so c1 is equal to what? Dm by dx. Okay, then we integrate again. Let me put the integrate outside. Okay. Then we integrate again. Okay, so now we have m as a function of x is equal to minus, no, I'm going to do the same, minus omega as a function of x. You integrate twice, dx plus by c1x plus by c2. Okay, so what you can see down here, right, from here, what you can see is the boundary condition. Okay, the boundary conditions, we have two, are used to determine C1 and what? And C2. Okay, the boundary condition are used to find what is in C1 and what is in C2. That is why, okay, you have to know this is the purpose of the boundary condition. Like the example over here they give you in math, what does it mean? All these are boundary condition. Okay, math is a language. Okay, so what we have done, that what we are going to do is to find omega x through the mathematical expression later on, okay, or through the figures of the distributed load. Okay, so let's start. Okay, so now we have to find the equation of the distributed load. Okay, now I want you to pay attention to the axis that I'm drawing now. Okay, right, so the first thing is we're going to find equation of distributed load. Okay, so I'm going to draw a graph now. Okay, so now this is x, right? This is omega. So you have 6,000, 12,000, 18,000. Okay, so you have 0, and we're going to stop at 6 because the length of the structure is 6 meters. And then the structure start at 6,000 in terms of load and stop at 18,000 after a distance 6 meters away. So now we are going to find, okay, so this is where we have our omega as a function of x. Okay. So we know there's a linear function. Okay, so linear function. Right. So this will be equal to y is equal to mx plus c. Okay. So we know the y-intercept at 6,000. The gradient we don't know yet, but it's a simple calculation over here. So omega as a function of x is equal to, so the distance from here to here, right? This distance is 12,000. The distance from here to here is 6. Okay. So from here, we know that this is equal to 12,000 divided by 6. Okay. X, okay, plus 6,000. The y-intercept is our 6,000. Okay. So this is our gradient. This is our y-intercept. Yeah, as you can see. Okay. So from here, you have omega as a function of x. This is equal to 2,000. Yep, 2,000x plus by 6,000. Okay. So we have done the first part already, right? We have found so we have completed with the what? We have done this. Okay. Then we substitute into dv over dx is equal to minus omega x. So all you need to do now is minus 2,000. Don't forget these steps, okay? Or not everything will go opposite. Right? So when integrate, you look at this, such simple integration, yes or no, right? So v as a function of x is equal to minus 2,000 x squared over 2 minus 6,000 plus by c1. Okay, so I will let this be our equation number 1. So equation number 2. Then from here, right, we got yes.
Sir,
Yes.
wouldn't it be 6,000x?
Oh yeah. Today what's your name? Where are you? Oh, I know
I'm
you.
Justin.
Yeah, Justin. I owe you more beer, okay? I'm just rushing now. Plus by C1. See, I told you guys, right? You guys know integration better than me, but there was a careless mistake on my side. So from here, we know, based on a boundary condition, we know that when x is equal to 0, v is also equal to 0. Okay, so let me quickly refresh in our diagram. Okay, boundary condition.
Yes, sir.
Yes,
Is V equals to 0 or C1?
v equal to 0. That's where I'm showing the boundary condition. Okay, when x is equal to 0, v is also equal to 0. So we have used this boundary condition. So it's a good practice is when you have to use the boundary condition, you highlight it, because you cannot use the same boundary condition twice. Okay, for this case. So you highlight it means you have used it. Okay, so you have used x equal to v equal to 0. So from here, right, so you substitute. Right. So you substitute into equation 1, right? So you have 0 equal to 0 minus by 0 plus by C1. So therefore, C1 is equal to 0. Okay. And then equation number 1 is also equal to what? dm by dx. Okay. So if we to look at our solution procedure, where are we now? Okay, so we have done this already. We have substitute. Okay, we already found the equation of distributed curve. We have substitute. We have integrate once already. Now we're going to integrate the second time. Right. So this is m as a function of x. So this will be equal to minus 2,000 x cubed over 6. Right. Minus by 6,000 x squared over 2. C1 is equal to 0. You can drop it. So now plus by C2. Okay. And then this is our equation number 2.